The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to today's Tech Talk on commissioning pressure critical rooms. My name is Sherry Adams, and I will be the moderator for today's session. Please note that throughout the Tech Talk, all phone lines will be muted. This will minimize any background noise or feedback that could distract from the presentation. When you first joined the Tech Talk, an attendee control panel appeared on the right side of your desktop. On the left side of this control panel is a small tab with an arrow icon at the top. Pressing the icon allows you to minimize and maximize the control panel. When maximized, use the control panel to submit questions. We will be gathering your questions throughout the Tech Talk and we'll leave a little time at the end for Q&A. If your question is related to a particular slide, please include the number of the slide in your question. A PDF of these slides presentation will be sent electronically to all those who register for today's Tech Talk, and we'll also be recording it, and it will be available on our website under the resource section. There is a password to access the Tech Talks, and that'll get sent out to you along with the presentation. Well, today's presenters are Jim Feeney, Kurt Matson, Stacy Carey, and Steve Yerge. Jim joined Grumman Buckus Associates 3 years ago as a project manager. He's the past president of the Central Chapter of the BCA. His earlier career was spent designing hospitals, labs, and clean rooms. Now he commissions them. Kurt just had his 10-year anniversary at Grumman Buckus Associates this year and is an associate with the firm. Prior to GBA, he spent 9 years at a large mechanical contractor and another 2 at a local design firm. Stacy and Steve are joining us from Midwest Associates. Midwest Associates is a commissioning and tab firm located in Indianapolis, Indiana. Stacy is president of the firm and is also a member of the BCA Central Chapter Board. Steve is a NEB certified tab supervisor and has served in the tab industry for 36 years. So Jim, I'll turn this presentation over to you.
Thank you, Sherry. This is Jim Feeney, and our idea for today is similar to a panel discussion that you might see at a conference, but we're going to do this remotely. We have 2 different offices working together. So get started. I won't read this whole thing, but the course description is pressure critical rooms, and emphasis is on critical, when the pressure has to be maintained. So we'll be talking about the lessons we've learned, and what we are doing today is creating a document you can refer to later. We call it a leave behind. We call it lessons learned. So when you get to your next job that has one of these type of rooms, go back to it and see the detail that we've included in it. So the C makes commissioning important for BCI. It's critical. It's critical because the consequences of failure are so high, either in cost, in money, or in delay. They're just not tolerable. So that's when you get identified a room it's critical, as opposed to a room that's pressure controlled, but maybe it's not critical. Say like a toilet, or say like a kitchen. There's some rooms that we just balance to a differential pressure, but it's not critical. So an example of a critical one is when you have no punch list for this room. All the bugs worked out. It's not satisfactory to the client that you've got a few items to work out before they have their first surgery in that room. That's not allowable. So the other thing is that because these cost a lot, they often are places where the MEP design is innovative. So they're trying new things. They're on what we call the bleeding edge of technology. And that's where we need to help the design team avoid mistakes that we've seen elsewhere. So where do you find PCRs? Hospitals have quite a few, ORs, liver rooms, ICUs, protected environment, patient rooms. And these are to stop the spread of infectious disease. Hospital pharmacies, of course, where they mix compounds that have to be kept pure. Central medical and surgical supply is basically where they clean and where they keep things clean and to avoid infectious disease. Then you have labs, biological and chemical laboratories, and generally they're dealing with some very nasty things, so they want to prevent that from getting out through airborne methods. That's how you can do that, partially by controlling the pressure. And then clean manufacturing, semiconductors and pharmaceutical, and that's all about maintaining the product quality. So one of the things I want to highlight, and I'm just leaving this behind, there's a new pharmacy code. It's called USP 797/800, and it's not known by everybody. A lot of design firms still haven't caught up to this, but it has a lot of information. So if you see a pharmacy in your facility, go back to this slide and then look, and also Google USP 797 to find the information. One of the things that I really like about it is the first time you see a code where they actually define what the architect has to do, and it has some really good guidelines that you can apply to any space that needs to be pressure controlled. So the other thing I want to talk about is tightness, and I'm showing a formula up there, but I don't want you to get too concerned about it. The main thing is that this is often what's used, and it's not really a calculation that you can actually perform, because the A, which is the crack area, it is so hard to determine. It's got to be kept to the lowest by the architect's spec. And if they don't, then the Q, which is usually our side, the HVAC side, has to get bigger. So I just want you to see this formula. The bigger the A, the bigger the Q is, to maintain the same DP, which is what typically we have a criteria for. So alarms go off when you get below 0.01, positive in OR, for example. So the one thing also cautions is don't get tied up with an engineer trying to calculate this, and then he puts in a transfer grill or something the size of A. Now, A is not really calculable. A is pretty much what you have when air moves through all the materials, every crack in the drywall, every conduit that's not fully sealed, all that stuff. It's impossible to really calculate. So my main takeaway is you can see the bigger the A, the bigger the Q. So the room is not tight enough. The HVAC system may not have the capacity to overcome the leakage. So one thing I've seen recently is a spec that's on one of my jobs, and I have it highlighted in yellow, but essentially they have a spec called pressurization construction criteria. They're actually telling the contractors how they want the room to be built. And that sounds like a no-brainer, like why don't they always do it? But they have it. This is something that I'm seeing new for the first time. And it's recognized that if you don't have the room tight, you can't have the exhaust system, or you can't have the supply system big enough to overcome it. And we'll get into that example. So one thing I want you to know is look for the specs of the architect, not just the mechanical. Look for the architect, because that's key. Some things here was from a recent lab, and I'll go through it again. Don't worry about catching everything I say, because you'll get a PDF version of this. So some things to look for is they have the wrong hood type in a non-chemo room. They had lack of coordination between disciplines. This first one I'm highlighting, return air terminal boxes were shown backwards. We had workroom and gowning design more stringent than required. Pressurization was not correct. Pressure monitors not shown. Transfer duct shown in gowning. Fire dampers and the hazardous exhaust. No sequences. I mean, these are kind of common things, but quickly, I'll leave this behind so you can look for some things. But it's kind of thing when you start looking into these type of rooms, you have to be aware of all the things that can make it fail. Basically, it's not just the amount of air that goes in and goes out. So another thing happens is when you try to put a pressure control room into an existing building, often this project, they had a non-ducted return system on multiple floors. So they're bringing the air back to a shaft, and they tried to put in a pharmacy and they couldn't control the pressure. What we ended up doing was putting in basically a return VIV box at the shaft so you can control the pressure from that room, and then added some exhaust fans for just a pharmacy. So it can be done. So some other thing I wanted to cover, and I'm going to look at the time because I'm trying not to take it all on this one. Door sweeps. I'll leave it. Sometimes door sweeps will work against you. So we ended up having to recommend taking them off, and it's because the pressure was actually going the opposite direction when things started opening up. You know, this is a leave behind to have you guys study later. Alrighty. So something that should be real clear is the drawing should show where all these pressure monitors are. And they normally are now tied into the BIS for alarm, but you'd be surprised sometimes they forget to say the obvious. It's not enough just to have an alarm visually or audibly, you know, right at the door. The nurses will hear that, but the BIS often has to have that to respond to something going on with the mechanical system. And then to avoid the nuisance alarms, always suggest that you control to a higher point than the alarm set. So for instance, if the alarm is going to be set at 0.01, then control to 0.03, and then the fluctuations will maybe drop it down to 0.02, and you won't be getting these nuisance alarms. And that goes for any type of room. Always be a little bit above it, but not too crazy above it. And there's a lot of information on here, but mainly I want to go through the points over on the left of the screen. Typically what we see is the supply box maintains the constant required airflow. So for instance, if it's an OR, you want 20 air changes an hour or whatever the setting is. And then second is the reheat coil valve modulates to control temperature. And then the return box maintains offset pressurization. So this is basically you just go from supply to return box. And I'll say right here, if you're trying to control the pressure of a room, you must have the control on the supply and the return. You can't just supply the control the pressure on the supply. You have to have them both. And then obviously if there's exhausts involved, that as well. You can't just do one side. And this has a lot of information on it. Pretty much it was the end result of what happens when they didn't. Is that the room, we weren't able to dial back unoccupied mode. And we're at 20 air changes per hour on this. And when you unoccupy, there's no real required air changes. Basically, you have to maintain pressure, and you can maintain temperature, humidity, whatever, but you don't have to have the air changes because there's no operating going on in there. But we're only able to dial it back to 12 to 15, so that's a lot of energy waste. So even after a lot of trouble, repairs, we only got it down to 8. And typically I've done jobs where we got it down to 5 proper. So that's where the architect and the general contractor, all those guys don't do their job right. We can't meet our energy goals. Basically, it's a failure on that. And I'm talking about on the design side and in the commissioning side, being with them on that. And then here, my last slide will be that Sometimes you need heavy-duty volume dampers when you have HEPA filters and fume hoods. HEPA filters easily can have an inch of static pressure. They will offset they basically will, the air won't go through them obviously, and they'll be drawing too heavy from the other rooms. So when you have like a lab, a university, or someplace like that where they're using one exhaust system and drawing from some hoods and drawing from some registers that have no hoods on them or no filters on them. First thing you want to do is advise they don't do that. But if they do it, they want to use one system, then they have to add heavy-duty volume dampers on the systems that don't have the HEPA filters. So you can balance them. So that's it for my slides. And now I will turn over control to my partner here. And I'm seeing, how do I move it over to Sharon? I'm sorry, here we go. Little buttons. Change presenter to Kurt. Yes, Kurt, you should have it now.
Can you see my screen?
I see you, great.
Okay, so this is another design thing. I'll be quick on this. You'll see this on maybe isolation rooms with just an ante room or maybe small pharmacies. This is a negative containment isolation room, which is obviously supposed to be negative. The ante room for these spaces, they don't really have, there's no requirement they could be positive or negative depending on the owner's requirements. And one thing to keep in mind here is, so this is a client who likes the ante room to be positive. So their typical design is one supply grill in the ante room. The problem the one thing to keep in mind here is in an isolation room, a negative room, we can make a negative room look negative across the store by either making a negative offset in this room or by making a positive offset in the adjacent room. So what can happen here with only a supply is this supply diffuser could actually be providing the major portion of the pressure pushing against the door. And if you do an egress test where you open up the ante room to corridor door, then the pressure here gets lost and these negative isolation rooms can lose containment. This is a common thing that we see, and sometimes we'll follow a balancer after they balance these rooms. And then when we do an egress test, we find that the negative rooms lose their pressure. This can also happen for negative rooms. I'm going to kind of skip past that, but basically the same thing for negative rooms. One thing to do with a negative room, if you have like a cascading negative pressure from a corridor to the room, you can make the ante room neutral by having a supply and return and using the negativeness of the isolation room to pull all of it through. Was a double. So back to the criticalness. So it's not just pressure critical, it's critical. These are typically kind of the most revenue generating spaces in hospitals. So if you're doing a replacement hospital, maybe you've got a few months to kind of get the bugs out of some of these rooms. But if you're just doing a pharmacy renovation in an existing hospital, or some sort of clean room or lab in a hospital, there might not be a lot of that kind of buffer time. So one thing that we do in our critical projects is we kind of do, if you've heard of pull planning, where you kind of do a schedule with all the subcontractors, but you start at the end of the project and work forward. Well, even when they do that, they typically still don't give very detailed end of project schedules, basically where you start having equipment startup, test and balance, controls. So as part of our commissioning effort, we'll do pull plan. We'll do kind of like a pull plan with just the contractors, and we pull from turnover just to where equipment startup is. And on this was going to be an FDA certified clean room lab. So we did a day-to-day schedule for like the last two months here. And we ended up with one major problem. An air handler came with the cooling and heating coils flipped. Which is kind of typical, when the air handler was delivered, the contractor kept it locked up for a few weeks. And then when they finally unlocked it and everyone got inside, we saw the coils were not in the correct spot. We didn't really get all that anxious. In our next meeting, we got together. We found on this schedule where we had 7 business days of time where we could get that fixed. So in 7 business days, we had the out-of-town design engineer fly in. We reviewed it. They provided direction, and the contractors had made the corrections and rebalanced the unit all in 7 business days. So it might not have worked so well without kind of having one of these schedules put together. Another thing to kind of plan for these rooms is to work with the engineer of record and put together kind of a little matrix like this. So here you've got the supply design CFM, but when you're going to be adjusting airflows for pressure, you kind of need to know what flexibility you have. So what we usually request is a spreadsheet from the engineer that gives us what the airflow rate is relative to the air change rate required. So you can see some of these rooms, we weren't going to be able to adjust the supply, but we could in some of these other rooms. So this kind of gave us, it allowed us to kind of do some planning with the balancers on what rooms we could do, what rooms we could adjust. So here's just kind of a couple items here. So another recommendation is bring the certifier in early, the hood certifier, the lab certifier. If there's a validator, bring them in. Who's going to be doing the terminal cleaning of the lab, bring them in. You know, they're all kind of experts in their own, and they all have little things that they can kind of bring up to the team. Even the cleaning crew, we brought them in ahead of time, and we found a few things where we had to caulk behind hoods and stuff based on the cleaning crew's requirements. Confirm with the engineer of record about what the final intent of pressurizations are. Even though you might get a drawing from the design team, it could be wrong, or the users might have a different interpretation of what they want to do with some of these rooms, and the pressures might need to change. Confirm user pressure monitor settings. Some of these clients might be getting a pressure monitor for the first time, or they might be getting some of these newer, more complex ones for the first time. So kind of try to get the settings that need to be put in place ahead of time. Door sweeps, door gaskets, sliding door tracks. Work with the general contractor to see what type of devices they're putting in, how they're adjustable, whether you need a manufacturer rep out there to adjust, say, a sliding door track. HEPA filtration, so our fume hoods, some of our biosafety cabinets, they're going to have HEPA filters on them. They have a pressure drop on the system, but a lot of times they don't put the HEPA filters in until the room is clean. So just coordinate with the general contractor when the room is clean, when the filters are going to install, and how you're going to do balancing and pressurization, because you need those filters installed. Fan filter units, determine how they're going to be adjusted and what controls they're going to have in place. So again, from an adjustability standpoint with the balancer, is it going to be manually adjusted with a potentiometer? Are they going to have a remote control system? A couple items there. All penetrations are sealed. I think a lot of different references you can see for all the different issues you could find with penetrations. And then equipment layout with low return exhaust grills, how equipment lays out with them. So here's just a picture of a CRC. This is a CRC, happens to be the example here of a pressure monitor. Some of the various things that you can edit. We typically set up these ourselves, so we work with the owner to kind of determine how they want to set those up. You got the room name, a secondary room name. The colors are adjustable. What you call these positive, negative pressures and these precautions. Precautions are more for isolation rooms and healthcare. But yeah, work with the users on how they want to be set up. Again, I think the important takeaway here would be alarm set points. Isolation rooms, ORs, their minimum is 0.01 negative or positive. Clean rooms might be 0.05. Just because those are kind of the guides or the codes doesn't necessarily mean what the user wants the alarm set to. So work with those alarm settings. And the delays, how long, like if a door is going to be open, how long can that panel stay in a warning before it actually sends an alarm out? And whether that alarm is supposed to be audible, because all these are usually adjustable in all of our the pressure monitors you're seeing nowadays. Here's just a couple examples. This, I think, is an Obstetra style where you have the transducer inside the pressure monitor. So you actually have to pull the pressure monitor off the wall to get to the tubes. If you've got some of the newer ones where they use more of an industrial type of pressure transducer, these pressure transducers are typically going to be in a box in the ceiling right above where this location is. And I show this because sometimes we might need to calibrate or re-zero the pressure monitor. My one recommendation here would be if you're going to try to re-zero a pressure monitor, some people will just open up a door and hit the re-zero button. My recommendation is pulling the tubes from the transducer and maybe even connecting the tubes together and then re-zeroing them. You'll find that even if you just open up a door, you're not going to properly re-zero it, especially with some of these very sensitive industrial level ones. Just here's some doors. So here was a pharmacy, and they had saloon-style doors with a big opening across the middle. That got nixed as soon as we saw that. And then we talk about door gaskets and how doors can be adjusted. That's me in a clean room. Right behind me is a door that is a sliding door. And behind this stainless steel box on top is the track. That track is adjustable. These doors can be lifted up and down, and they can be brought in and out from the door. So this is where we'll actually talk with the general ahead of time, because from some of the clients I have, we will actually pull these panels off and we will adjust these doors ourselves. We talk about the tightness of the rooms. We like to have the room to start as tight as possible, but a lot of times we've got to loosen it up when we're doing the balancing or when we're doing the pressurization. And we're going to do it by adding more gap across the bottom of the door, or we'll pull the door off, we'll pull it right off, and we'll pull the gaskets out of the door, and we'll cut the gaskets and slide them back in. That's kind of some of the ways we do a lot of our clean rooms, especially with cascading type of pressurization. And here's just a quick thing with gaskets, door sweeps. If you are going to be putting door sweeps on, our recommendation is the single blade type. These are the drop type ones. The problem with these is they're not repeatable. Over time, when you close the door, these sweeps don't drop the same way every time. So they can be problematic. And these sweeps are, they're about 1/4 inch adjustable. Plus you can slide these gaskets out of the frame. You can cut the gasket down and slide it back in. Here's some fan filter units, just a couple things that we like to look at. This thing will be up for future, but challenge ports is basically how the certifier is going to test it. They spray an aerosol into the hood, but they got to have access to the upstream side of the filter. So there's this little challenge port that you can get from the factory. Some users like to see these remote control panels. Otherwise, you can do these just magnet helix outside of the room so that they know that the filters are getting dirty. For the balancers, make sure that this is the side of the unit. If it's going to be manually controlled, make sure some of these potentiometers are accessible. The proper torque settings of these fan filter units. If these fan filter units are recirc, or if they're going to be tied in with the VAV box, their motor and torque settings on these ECM motors are different. So it's something to work with during the design phase or during construction. And then all these fan filter units you're going to see come with this pre-filter on the inlet side here. Some manufacturers tell you to remove them, some tell you to keep them in place. So just be aware of that. Here's where we talk about kind of when the users are going to be putting their equipment in. Kind of here's your typical you find anywhere: thermostat, refrigerator, thermostat, laboratory heater. Now here's one we found in the pharmacy that we came back from a warranty issue. They were having some weird pressure issues, so I just sat in the room and watched them for an hour and found that they were putting carts up against these low returns, and you can see the plastics getting pulled into it. And then the gowns were actually being pulled into the returns, affecting pressurization. Here's another example here. I might not go too deep into it, but we just talked about sealing it. This is one where we had a corrugated ceiling, corrugated decking for the ceiling. A lot of times you're going to talk about this, making sure that the corrugation is sealed up. But the other, which is, I'll say, somewhat easy to do, the difficult part is every penetration through that corrugated piece of metal has to have this like wonky ceiling. Sometimes you have leaks and you've got to go up there in the dark and see sunlight come through. If you need help finding it, you can use these smoke tests. Here's a video of no leak, and here's a video of a leak. You can see it being sucked right in there. So we took about this actually took about 3 days. We had to keep this. This was a lab where they are cracking open dinosaur bones, and we did have to keep it. We turned it over about 3 days late because we had to find all these leaks. This one you guys can read about a little bit later. This is actually that ancient DNA dinosaur bone. It's an interesting thing that we had noticed about the fan filter units. So, here we go. Stacy?
Okay, thanks.
Good afternoon. One of the things, when it comes to test and balance, what we've always got to remember is what we're trying to achieve, whether it be a positive room or a negative room, and of course all the requirements around it. Like's been said, integrity to these spaces is everything, and the ability to make these rooms positive and negative can be challenging. But one of the things that we always do is pretty much sit down, look at our drawings, look at our specs, and understand our requirements. Sort of not question the engineer, but go back and review and make sure that our numbers are correct based off the cubic feet of the room and so forth versus the airflow, whether once again it be positive or negative. After you've got a handle on your project, what you're trying to achieve, usually inspecting the room is always something that you need to do, go around looking for the various little things that possibly may have been missed during the construction and setup phase. But for instance, if we're going to go for a positive room, what we got to remember, our dominating factor is the supply. So a lot of times you're going to get those set up as far as your supply numbers, because the room's got to be positive. And typically the numbers that are being put on the return, as far as the returns or the exhaust, I don't want to say they're a guess, but once again, going back to the previous stuff, it's a baseline. Knowing that our supply, being a positive room, is pretty well etched in stone to maintain our air changes per hour and so forth. So our variable in a positive room, after we get it set up, would be the exhaust. So you get your supply set up to your design, you set your exhaust up for your design. Let's say you're not making that differential pressure. So the integrity plays a role in that, door sweeps and so forth. So you can have a little play in your exhaust to vary from the design criteria as far as the design numbers to achieve that. A lot of the things we find is, like the pressure monitors not being in calibration. Verifying that, once again, Kurt, you know that very, very well, talking about how to make sure you're zeroed out and so forth like it, and taking your differential pressures after you get the room set up. I'm trying to not get too crazy, but be a little bit more, specific on test and balance. One thing on this first page, on page 30, there is an error down there on air change per hour. It should be the total supply or exhaust times 60 divided by your cubic feet, your room cubic feet, to come up with your air changes per hour. In multiple room cascades, and test and balance can really get tricky because, like hospital rooms where you have your central sterile, which is typically in the center, which is going to, sort of cascade out in different things. Clean rooms, your most inner space is your most critical to start with, and work your way out from there. You're going to be going back and forth several different times in adjustments. You make an adjustment in one room, how it affects the pressure and cascade of another room. I mean, it can get pretty back and forth. I find a lot of, once again, we're generally working with positive rooms, get your supply set up first. That is your pretty much defined number, and then adjust your supply as need be after you get your baseline. We can jump to the next page. This is just a representation of a typical balance report, what we use. It's really nothing fancy. The nice thing about computers today is like on our air changes per hour and so forth, we can put the little formulas into the spreadsheets, and you're just typing in your numbers, and it will kick out everything for you as far as your air changes per hour and so forth like that. What we like to do is do a nice little picture with our directional airflows, our room pressures, and then also our differential pressures at the bottom of the report, like this. And this one here is C291 to C2187, being negative, and to the corridor negative. Typically, you're going to see, this was a little bit different, but typically you're going to see a differential pressure there. A lot of your things today are working on 0.01 negative in negative rooms. Equipment can be one of the things that really needs to be looked at pretty hard. A lot of times you're walking in, you're just doing one area and not really dealing with the HVAC equipment directly. So with us, we typically like to go see that equipment anyway and make sure, you know, where it is, if the exhaust, a lot of times like isolation rooms on exhaust fans. Typically exhaust fans, each group or individual isolation room is going to have its own exhaust. Sometimes they're HEPA filtered. You just really need to understand your design of your system as a balancer for filter loading, especially on exhaust. Coming up with that design pressure, static pressure control for your exhaust. As filters load up, airflow goes down. So it's very important to understand how those systems are working, whether, once again, be the positive room or a negative room, especially when we have HEPA filters in those spaces. So, and some of the lessons, if we can jump to the next page, some of the lessons that we've really learned, in most cases, the initial balance to design airflows doesn't achieve required pressures. Discussed adjustments with the engineers. You know, a lot of times, you know, we're searching and finding. We hit our baselines and then making adjustments accordingly once again. Most balancers will measure rooms dimensions without taking cabinetry, bulkheads, and so forth. What we've always looked at, especially when you have to meet air changes per hour, we try and use the raw dimensions of the room before we start taking out bulkheads, cabinetry, and everything else. We always figured if you can make it with a raw room, you're actually giving a little extra air changes per hour for that room. Like always, verify that your CAD equipment is in calibration. Hopefully we do that before we got on site, knowing that our equipment is in calibration. A lot of times in isolation rooms, low level exhaust, especially when you're going into re-verify, a lot of times here, depending on which hospital, it's every 6 months or every year. Low level exhaust can really be a hindrance, especially with all the linen and so forth like that. One of the first things I've always done when I walked into the room, that was the first place I went, is those low level exhaust. Because a lot of times they're drywall ceilings, you really don't have access to dampers, and they're notorious for putting OBDs or opposed blade dampers behind the grills. And those things do load up. So typically, that was the first thing I did was go in, pull the grills and clean them. The other thing about exhaust with turn vanes and elbows, something you can't see, but we find that through the years, these things will load up and they will start really, you know, cutting your exhaust down into the space. So that's something to be aware of if you're going back to these rooms multiple times through the years. You know what to start looking for, and you know what your exhaust has been doing all these years, and all of a sudden it just slowly starts tapering off. It's something else to start looking at, doing static pressure of the profile of your ductwork or whatever to find, you know, those obstacles. And that's, oh, the other thing, especially in isolation rooms, is your restrooms. Typically, all isolation rooms a lot of times have your restrooms in them. You always need to make sure those restrooms are negative, typically tied to that exhaust system, and you're meeting your design air changes per hour. So those are some of the things that we really look for, is making sure those restrooms are good, making sure they're negative and so forth like that, and making sure your differential pressures are correct. And also, one of the main things is making sure your monitors, differential pressure monitors for the users are reading accurately. And one of the better things to do is if you've got a set point, like a 0.1, you always want to move that up a little bit so you don't have nuisance alarms. That's the worst thing that you can have. But we got to remember too, a lot of these rooms today, they can be positive or negative with a flip of the switch. So, or in the unoccupied mode. So you could be setting these rooms up in a multiple scenario deal. I know I don't like them. I like to see, myself, it just gets too cumbersome for the users. And the other thing too is if the users really don't understand those rooms, they're putting infectious patients and they're not properly setting those pressure monitors for positive or negative. I've seen that happen. So, but outside of that, that's pretty much all we have right here.
Thank you, Steve.
Thank you.
We got one question that came in, and feel free to jump in and add your questions. So this is for Kurt. It says, regarding calibration of the pressure transducers, what is the best strategy, aka for zero in the transit with doors closed to adjacent space or doors open?
Oh, gotcha. So when you're zeroing it out, I guess it doesn't really matter what you're doing with all the other doors. I would say because the best way to do it would be to find the transducer that's associated with that pressure monitor, go to the transducer and pull the tubes off of the high and low port. So then the high and low port, no matter what the other doors are doing, the high and low port are right next to each other. And I said to take it one step further is carry a small piece of pneumatic tube with you and connect the low and high port together and then re-zero it. Then basically it doesn't matter what other rooms are doing, whether there's a breeze, pressures, you're taking all of that out of the calculation. That'd be my recommendation. That's what we do.
Very good. Very good. I don't see any other questions just yet. Sherry, do you see anything on your side? I'm kind of learning this.
No, I don't see anything else. If there is a question, you have a moment to ask. I'll just quickly just remind everyone that the BCA annual conference is virtual this year, and it will include sessions starting every Monday in August, with a pre-conference workshop starting on Monday, July 27th with David Sellers. So there'll be details on the website and registration will be open soon. Jim, it looks like you have one other question, a couple of questions that have come in during that announcement.
Yeah, and I'm only seeing the one I just did. Let's see. Remove this line. Okay. Oh, okay. Thank you. What is typical criteria you're seeing for the negative pressure differential for a lab to be certified?
I think 0.05, if it's a certified lab, 0.05 from the dirtiest spot is the minimum requirement typically. So, or what I should say is it's 0.05. It's 0.05 between two rooms with different ISO classes. That's actually the best way to put it. So for every door you go through, like as Steve was saying, one of the labs we had on there as an example had 7 doors to go through from the dirtiest to the cleanest. It's a lot of rooms to try to figure out how to balance. So every time there is a change in ISO class, there's a 0.05 inch requirement between those doors. So the one thing to keep in mind is when you're looking at design drawings, sometimes some design engineers who are familiar and do a lot of clean rooms, you're going to see some pressure ratings that they're going to put on their drawings that might be like 0.15, 0.2, because what they're doing is they're putting the pressure referencing the dirtiest location. So that might be 0.2, but that's going through 7 doors and pressure may flip 3 times. You only need 0.05 across any single door, but if you see some of these weird numbers, that's because they're all referencing a common dirty point. So that's a good question for the engineer of record when you're doing, like, say, that matrix is, what's the engineer using as the reference?
Okay. A question for Steve and Stacy. Do you provide the map of pressures on all reports for projects with pressure critical rooms, or only if required by the TAB specifications?
Well, typically we'll show that on all our reports. Any type of pressure control on a typical balance, no. But when you come into pressure control or differential pressure that we know it's a code or it should be referenced, yes, we do put them on all our reports. Typically, we're going to draw a picture of the space with our differential pressures, show a general layout of the room with the sizes or whatever, how many supplies, exhaust, and actually, give that information. Like I've always said, looking at a balance report can sometimes be pretty boring. You're just looking at numbers, but a picture, especially when you're looking at pressure control, can make a big difference and make that report more understanding, able to get that information out of that report and know what it means.
Okay. So here's another question, I think from Mike Wolf. What is the best control strategy for unoccupied modes for critical areas?
Don't have them.
Don't have
It depends. So I think Jim kind of might have referenced some setbacks for ORs. We do setbacks for ORs. Typically, whatever the sequence is for occupied, the same sequence is for unoccupied. So whether it's control the pressure, control the offset. But one thing that you could do is if you're controlling to an offset, one thing to recommend early might be to tell the control contractor to have a separate point for occupied offset and unoccupied offset. I've run into plenty of ORs where we actually had to have a different offset when the air change rate changed for the setback. For something like clean rooms or other types of pharmacies, our recommendation is to not do any type of setbacks anywhere around those rooms. And kind of Jim had kind of referenced a little bit rooftop units and building pharmacies within existing buildings. Economizer mode, if there's anything going on in that building where the return airflow might change, one is a rooftop unit with economizer mode or having some types of airflow setbacks around the building. Not that you can't do it, but it's a concern you want to bring up to the team early on that you might want to design the unit to not have economizer mode or the capability of not having economizer mode. And you might want to talk to the user about disabling any type of setbacks or not having setbacks for some of these pressure critical rooms. Because like something like a pharmacy, the air change rate's so high, you're not setting those back at night. Because ORs have a different air change, because their air change rate, their minimum is low enough to where, at least in Illinois, they allow setbacks. But something like, say, pharmacies and clean rooms, they've got prescriptive air change rates, so you can't set those back.
Okay, we have a question from Paul Levy. What is the sensitivity of the transducer?
Ooh, that sounds like a control hardware engineer question. I'm not 100% certain with that. But yeah, like with some of those, like the old Siemens ones, the Setra ones, I think Setra actually made the Siemens ones. We find that I think they're actually replacing those now, but historically they've been problematic and they have to be replaced a lot. They're hard to re-zero. A lot of times they'll even come from the factory so out of calibration that the tech just tosses them. But now with some of the newer ones, again, Sierra happens to be one of them, where it's more of like an Ashcroft or Bisala type of pressure transducer. I couldn't tell you what the sensitivity rating is. but they're sensitive enough to where just opening up a door doesn't work, and you literally have to, like I said, connect the tubes to do a re-zero on those.
Okay, another one. For a positive space, is there a pressure that would be considered too high as long as it didn't adversely affect doors opening, etc.?
I guess I can take.
I can start with that. First of all, it
Yeah.
doesn't take much pressure to keep doors from closing. So that's what's the key. They have door closers on them. And there's ADA rules about how much pressure it takes to open doors. There's
30 psi.
Yeah, and that's a very, when it translate 30 psi to inches of water column, it's pretty low. It's, you know, I don't want to get into it, but it's, be careful of not just opening doors, but they won't close.
Yeah.
And if they're security doors and they don't quite close, then you don't have any security. You know what I mean?
Yeah.
If you have, so I think that's probably the answer is
Yeah, it's
door
I
closers.
think it's 30. Yeah, we actually have door closers we bring around to job sites.
Mhm.
Stairwell pressurization, atrium pressurization. That's where those numbers come in the most. But it all depends. If you're, and that's why I say bring in the certifier or the validator ahead of time, because they're going to have a much better idea of what the users are doing in the space. And then they're going to be able to provide the users with much better feedback on what a maximum pressure might be. Jim was referencing USP 797 and 800. In the negative HD compounding rooms, they actually do have a limit. It's 0.01 negative to 0.03 negative. So 0.03 is the most negative it can be. And then for the other non-HD rooms or non-classified rooms, it's 0.02 is kind of a guide. One thing to keep in mind with regards to that question is if you've got a negative or positive pressure, if you open up that door, you do get that inrush of flow that you can feel. If there are hoods located near those doors, that inrush can actually affect the face velocity across the hood, and they can be problematic. And again, we have certifiers that can bring that up. They can do the cross the face test to kind of confirm that. But I don't know, 0.05 to me seems like when I'm doing ORs, I think Steve had said that 0.01, at least in Illinois, is what we have for ORs and isolation rooms. We try to hit 0.025, 0.03 as our range, and we try not to go above 0.05. At that point, you might have issues with doors, as Jim was referencing.
Yeah, the other thing I want to point out is that equation is square root. So you have exponential growth in the airflow you need every time you go up a pressure. So it doesn't sound so, oh, we want a pressure of 0.05. Well, when that takes twice the air as 0.03, then you start realizing, well, why am I paying that? Why am I doing that? And again, a lot of people don't understand when you've got quadratic equations, things go up real fast and become real hard to do with what you have. Then you waste a lot of energy too.
Yeah. And the last thing I'll say too is when we talk about how that inrush of air, that's kind of dependent on how tight the door is to begin with. So if you've got 0.05 across a door that's got a sweep and is super tight, as soon as you open up that door, you're going to feel the pressure and you feel that air rush in. But if you've got a door with a nice gap under it that you're maintaining 0.05, the nice thing about removing those door sweeps is that you don't have that inrush of air because you've already kind of introduced some crack area across the door. So when Steve talked about having to balance the cascading egress and ingress paths on all these labs, and kind of the what I was talking about with my clean room, usually you'll kind of introduce all the air at the most negative or most positive, and you actually use the doors gaps to balance the pressures across all the other rooms. If you have 0.05 or something across the door, as long as you have a big gap, you don't have any problems of opening or closing the door or having that inrush. It kind of depends.
Got a couple more questions. So as a follow-up, are differential pressure criterion typically in inches of water or PA or both? Since I work only in the United States, I've only seen water column, but
Yeah, I think some of those reference Pascals.
but we're often different. Yes, and sometimes both. So
Yeah.
the answer is yes.
Yeah,
It's both.
I did a
It
lab.
depends on who
Yeah.
you're talking to.
I did a lab where they actually requested the BAS automation system to show the pressure in pascals because they were from across the pond.
Yeah.
But yeah, I think it's something, I'm terrible with it, but I think it's like our 0.01 to 0.03 inches is I think 5 to 10 pascals, or 0.02 to 0.04 is 5 to 10. It's right around there.
Yeah.
That's the conversion.
So here's one for you, Kurt. Why do a variable return in a pharmacy instead of fixed CFM so that balancing is set it and forget it? Oh,
Yes.
no, I'm sorry. Why do a variable return in a pharmacy instead of a fixed CFM so that balancing is set it and forget it?
No, that's exactly right. That's what I mean for pharmacies, clean rooms.
You don't
you're
want
almost,
to be.
yeah, you're all, I mean, they may have VAV boxes, so I apologize if I say VAV.
Yeah, right.
That just means they have terminal units.
Yeah.
They're almost always going to be set for constant volume.
Yeah, the maximum ends are equal. You make a
Yeah.
VAV box into a constant volume box.
Yeah, the only thing that we really see variable now is ORs. Even in Illinois, isolation rooms aren't even allowed to be unoccupied anymore. But yeah, no, definitely, I agree. Fixed airflow settings.
Got the questions keep coming, I guess. So,
It's a good subject.
why do you typically see the airflow? No, I'm sorry. What do you typically see for airflow requirement per door to maintain pressure?
The rule of thumb we kind of have here in Chicago is about 100 CFM a door. So a double door is about 200 CFM.
Yeah.
That's kind of the rule of thumb we see. And actually, surprisingly, now after USP has come out, I've seen a lot more tighter rooms, and it's getting better than that. But for some of the other like large hybrid OR rooms, we'll see in excess of that. My rule of thumb with big ORs has been if after like a preliminary assessment, the offset is above 500 CFM, stop any of your testing, go back to the GC, the leakage. Once you start getting more than that in these rooms, you're now starting to affect the ventilation systems, efficiency, how it's got to bring in an OA or exhaust. So those have been kind of the rule of thumb we work with.
So Kurt, says, do you have any recommendations for field calibration of thermal anemometer? Anemometer.
Dispersion or thermal anemometer. Like for the
type room pressure monitors like the TSI for sure. Room pressure. Yeah.
So we we use a TSI. We have a couple TSIs here. Now our TSI though has an actual manometer ports on it. But we send our maybe I'm not fully understanding the question, but we send all of our, when we buy something, we typically buy it so that it can be calibratable. And we send all of our equipment out once per year.
Okay. So here's a question, maybe I'll help you. What are some of the most effective control strategies for overall building pressurization? Before we answer this, we want to be clear that building pressurization is different than critical room pressurization. And basically, usually it's not critical, number one. And usually you're dealing with the volume and construction and multiple doors. And you're at the air handle level. In most pressure critical rooms are at the terminal unit. Unless you're at pharmacies, we try to have their own air handler for them. Or ORs might have their own, but you might have multiple rooms. So other than that, I would say
Yeah, I think this is one of those you ask 10 engineers to get 15.
Maybe
answers.
it's another topic, another tech talk topic, I think.
Yeah, I mean, when it's a rooftop unit, you're kind of married to their building pressure sensor, because that's just how they
Okay.
control the return fan.
So we're running out of time, so I wanted to get to the next one. For spaces with VAV boxes, controlling supply exhaust is single point or multiple point calibration better? So I'm reading like 2 lines at a time, so it's a little hard to get. Are all VAV
Okay, I don't know, Steve,
control?
I know like when we do VAV box testing or calibration, I think typically you're just doing a single point calibration at the design airflow. Do you ever do a calculation for a VAV? I know for airflow stations, but for a VAV box?
Yes, typically, being a constant volume, we're going to, like any VAV box, or I should say CAV, because we're typically talking constant air volume and pressure control, short of doing some type of offset between the supply and the return if you have variable volume, which once again, don't see that a lot in any type of standard pressurization unless they have some type of night setback or something, which is very, very rare. But typically it's a 1-point calibration. And a lot of the controls, you're only doing a 1 point. The minimum is going to somewhat be what it is. So it really depends on who that control contractor is too. That makes a big difference on our abilities to calibrate.
Yeah, but I will stress if this is related to say like I know an Ebtron actually has in their calibration wizard a 2-point calibration setup. Yes, if it's an Ebtron, use the 2-point calibration wizard. You will have issues if you don't.
Hey guys, we're going to have to close, but that was the last question. Thank you. I want you to see on the last slide our phone numbers and emails, and feel free to send us questions if you have any, and we're glad to continue this discussion through that.
Yes, I wanted to say thank you, Jim, Kurt, Steve, and Stacy. We really appreciate your time and expertise. And like Jim said, if we have more questions that come in, feel free to email them or email me, and I'll make sure I get the question over to them and get your answers, get everything answered for you. So on behalf of the BCA, I'd like to thank everyone for your participation in today's Tech Talk, and have a great day. Thank you, everyone.
Thank you.
Thank you.
Bye.